Okay. So we will study about how the sinusoidal voltages are generated first, or else somehow we have this further as well. What do you mean cyclotron? What do you mean cyclotron? What happened? Is that cyclotron? What does it mean?
Sir, I'm asking if that figure B is cyclotron, sir.
Okay, okay. It's just simple representation of a generator. That's it. So constructionally for a machine, right? What are the components you have in a machine? In the morning, we were talking about some machines, right? So what is it? Fine. Machines can be classified into two types. One is motor and one is generator. So what are the fundamental components of in the construction of these elements? What are the fundamental components you can see for either for a motor or a generator, right? So what is a one second. Yeah, you can shade. Yeah, we are talking about this, right? Okay. What are the fundamental components in a motor? Any either a motor or a generator consists of? You will be having only two elements. One is stator and one is rotor. So what does it mean by stator and rotor? See, these elements are we already we will discuss the same thing in unit 2, unit 3 and unit 3 and unit 4 as well, where we discuss about DC generators and motors, alternators as well. So I just want to give a glimpse of what are the components we study in the coming classes, which are required for now to learn about the generation of sinusoidal waveforms, right? So what do you mean by stator and what does it mean by a rotor? What is the definition or meaning for these two could be? Stator or rotor? Rotor being the moving component and stator is the stationary part, right? That's fine, right? So in the previous figure we have, which I have shown, yeah, number 27. You wish to say something? So assume that this is a circle and this be the let this be the right. So let this be one of the part, right? Let me say that this is a stator. So we know that you have a stator, you have a rotor, right? So let this be the stator. Let it be assume that this is a good circle, fine. And what about the rotor? Let this be the stator, right? Which is a stationary part which has a firm fixation here, which doesn't move, right? And what is the rotor is the space in between the rotor or inside the stator, there will be one rotating part, which will be something like this, right? Which has to be hung between two, say, two ends. Suppose if this is the front view, what is the side view could be? How the side view could be? I think you don't have an engineering drawing where you can see the front view, side views, right? So let this be the side view, and this is a shaft which comes out. No. I think this is not required here because we are not. Let me draw it differently for this. So if I insert this rotor inside this, I think you will be having a structure like this, which you can see like this. This is a front side view, right? So this is a front view. And if I insert this rotor inside this, I think this will be something like this, right? And this is a shaft. So this is a shaft which is shown here, and this. So if I want to cut this, if I cut this, I can see a view like this. So this will be the stator, and this the this will be the rotor. I think I can draw it like this, different color. So what is the function? What does it? What's the need for placing those two elements? What does they do actually? Stator and rotor do. They are just meant for housing some wiring, housing a winding. That is to place some winding within the stator and rotor, right? They are just to hold. Yeah, they are just to hold some windings. So what is the need for winding is to provide some magnetic field, right? So if we can elaborate this stator, right? If you can redraw this stator, let me draw it for one case where you can. I think this will be an easy analogy for us to or method to remember this, right? Let me assume that I have two poles, right? Let me assume this has two poles because we don't have minimum number of poles that exist are two. That is, we don't have a monopole. So definitely we'll have a dipole. So let us assume that you have a north pole and south pole, right? And how you get this north pole and south pole? By using some windings, right? You will be these two are not permanent magnets. These two are electromagnets. And you know how the electromagnetism comes into picture, right? So whenever a coil is excited with a source, right? It exhibits some electromagnetism, right? So when I give supply, what happens? These two poles will produce some magnetic flux, or you call this as electromagnets. So what's the function of electromagnets could be? Whenever they are excited, they will produce some flux. And we know that whenever we have a north pole and south pole, definitely the flux flows between these two poles. And let us assume that the flux flows from north pole to south pole, like this, right? So whenever we have such case, right? Suppose this hole will constitute a stator, right? What's the function of the stator is this? To form a stationary pole mechanism or stationary magnet, say stator field. Now, when we consider a rotor, what is a rotor consists of? Rotor consists of same winding. You will be having some slots here, right? In that slots, what happens? We will place some windings. Here in this, we can place some windings here, right? Here we can place some windings. So as a whole, what's the function of this winding? They are nothing but a conductor, just a conductor placed in the slot like this, right? So what happens if these conductors are placed in the magnetic field now? As according to the Faraday's laws, which we discussed in the morning class, what does it mean? What is the Faraday's law state? Is whenever a conductor cuts a magnetic flux, an EMF will be induced in it, and such induced EMF is equal to n d phi by dt, right? Which depends on the rate of change of flux linkages, right? So this is a EMF generated, or else the magnitude of EMF given induced in the conductor given as d phi by dt. Now let us see that this conductor, right, from the front view, how will be the from front view? It will be just like this, right? Circle. So assume that you have a conductor here, right? This conductor, let us say that this is placed on a rotor. So what will happen if the rotor rotates? The conductor rotates. Let us assume that this conductor A is a conductor which is placed here, conductor A here in this slot. So what will happen when this rotor rotates? When this rotor tries to rotate, what happens? It's just like rotating the conductors as well, right? So don't for a simplicity, let us consider that only one conductor is present here, conductor A. So this conductor A will be, if I make it to rotate a 360 degrees over in the magnetic field, right? What will happen now when it is, let me consider some instance here, when it is near to the pole, when it is away from the poles, and it near to the next pole, what will happen? What is the amount of that flux cut by the conductor? See, the EMF induced is directly proportional to the amount of flux cut, right? That is time varying flux, right? Now, what happens to the EMF that is being induced? What will be the value of this flux that is cut by this conductor? No doubt, at these points, at position 1, let me write this as position 2, position 3, and position 4. We know that since position 1 and 3 are away from both the poles, the flux that is linked with the conductor will be very less. But when it moves from position 1 to position 2, what is happening? It is moving towards the center of the North Pole. So it is cutting the flux while its movement, and it is moving towards the flux, higher flux densities, right? So what will happen is, and what are the flux that is cut by the conductor will be of this nature. So what will happen here? What is going to happen here? The amount of flux cut by this conductor at position 1 is 0. But as it moves from position 2, right? As it moves to position 2, it has cut some flux here. And we know that as it is moving from towards the center of the North Pole, the EMF, the flux cut by the conductor will be definitely large. And after up to 1 to 2, this will be the flux cut by the conductor. Now, what will happen if as the continuation as the rotation continues to from position 2 to position 3? What will happen? What will happen if it moves from 2 to 3? Will the flux go on increasing or it will decrease? It will decrease, right? Why? Because we are moving away from the right. We are moving away from the center of the pole towards the pole tips, right? So where this flux here will be definitely less compared to the flux here. So the flux cut by the conductor will be decreased to 0. Since I am considering position 1 and 3 are identical, the flux at position 1 and 3 will be also be same. And it was the flux cut by the conductor was increasing in nature while it is moving from 1 to 2, and it will be decreasing in nature when it moves from 2 to 3. Now, what happens when the conductor cuts the flux from 3 to 4? What will happen? What will happen when the conductor moves from position 3 to 4? What will happen? Just tell me what happens if the conductor moves from position 2 to 3 to 4. So the current flux increases in the negative direction. The graph increases downwards. But what's the reason why it going in the opposite direction? What could be the reason why it goes in the opposite direction? What could be the reason why it goes in the negative direction? No doubt the flux from position 2 to position 4 will be increasing in the negative direction like this. So this is a instant, fourth instant, right? So, but why does it increase in the negative direction? Why can't I assume that the current flux will be in this direction? Why only in the other direction? Why does it go in the negative direction?
Because the flux density is decreasing.
Okay, flux density is decreasing, but why it goes in negative?
To show that decreasing, we represent it as negative.
Okay, that could be, might be, but exactly what happens here is, suppose if say from north pole the flux is flowing downwards, right? Isn't it? Now when it comes for south pole, the same conductor will say these two are identical, right? Section 1 to 2 and 3 to 4 should be identical. But see the direction of flux cut by this conductor in 1 to between 1 and 2 and 3 and 4, they are exactly opposite actually. Now the current has the flux, which whatever the flux that this conductor is experiencing from position 1 to position 2 is exactly opposite to the direction of flux that flows from 3 to 4, right? So definitely once if the flux is producing from north pole to south pole, definitely it has the direction will be reversed. So the resultant flux can be represented as further decreasing in the flux magnitude, or it is reaching to the negative peak, right? Similarly from 4 to 1, it is just analogy for section 2 to 3, and these two are same, right? So if I want to move from 4 to a, what will 4 to 1, definitely it is moving away from the pole to position 1, where the flux cut by the conductor will become 0. In this sense, what happens, the flux is increasing to a maximum peak as it moves towards the center of the pole, and it will move away from that. As it moves away from that, the flux comes to 0, and it from position 3 to 4 it goes to negative peak, and from 4 to 1 it comes back to 0. So what is the need for making it to vary this like, or else why can't we place directly at position 2? What happens if I keep the conductor stationary at position 2? Will there be any EMF induced in that? We should have a time varying flux, right? We know that whenever I give a DC supply here, suppose say if I give a DC supply here, the flux produced will be a stationary one, that is it flows from north pole to south pole continuously with a constant magnitude. But what we want to have a EMF to be induced in the conductor, we can't directly place the conductor in stationary field, but we has to cut the flux, right? Or it should have two properties: either the conductor cuts the flux, or the flux cuts conductor cuts the flux, or flux cuts the conductor. So EMF is induced only if there is a movement, right? Fine, good. So definitely there should be a relative speed or relative motion between stationary flux and the conductor, or flux and the conductor and the flux anyway, right? Whichever could be moving, right? I can keep the conductor stationary and can rotate the field as well. Both are okay, right? So that gives an EMF induced that is proportional to d phi by dt. Here see the flux, if I represent this to be flux, right? This is flux which is varying, time varying from instant to instant, it is varying, right? So have a time varying flux. Definitely what happens, there will be a similar identical voltage that can be found. So this is the identical voltage, right? So this is a equation, this is a representation for voltage. Since what is that? V is equal to, or E is equal to d phi by dt, right? So definitely the value of voltage will be proportional to this. In some cases, we can take it as a derivative of that. That is a, if I have a sine wave, I'll get a cosine wave, no doubt. Fine. It depends. You can, if you are, for just understanding, I just give the sinusoidal waveform, right? So definitely it follows either a sine wave or a cross wave, right? So it doesn't matter when how it goes, but somehow it will produce some alternating waveform. Am I clear with the waveform, sinusoidal waveforms? So whenever a current conductor is rotated in a stationary magnetic field, it will cut the flux in this proportion, and an EMF will be induced in that conductor, which is proportional to the rate of amount of flux that is being cut, right? So this is just an analogy, right? I'm just not giving exact solution where I can get a sine cos wave, right? But net change in flux is zero, hence no EMF. Where? Yeah, apply the dy by dt, then you'll get exactly what actually output will be. The result, you're not talking, we are not talking about the equivalent, right? From over a total time period. We are not talking about the whole time period. I just want to get the waveform, output waveform, right? So forget about the values which you get, say. I want to learn how the voltage is generated. Let us talk about the average RMS values later on. Okay. Yeah. So now we will move on to the next element. So this is how the sinusoidal waveforms are generated, and I already said in the last class, in the morning class, that once the voltage fed to the generator is, or fed to the load is following a sinusoidal nature, definitely the response, if the excitation is sinusoidal, definitely the response will be also be sinusoidal, right? So I have sinusoidal voltage, sinusoidal current, but what happens? What will happen when this current flows through pure resistor, pure inductor, pure capacitor? That is what we want to learn, right? But before going to that, let us study about some representation of sinusoidal quantities. And we know that we already studied that AC quantities are AC quantities are they scalars or vectors? Quantities can be of two types. One is scalar and another one could be vector, right? So what is AC quantity? Whether it might be, is it a scalar or a vector? What is the AC quantity? Which is alternating in nature. So we know that DC quantity is a scalar quantity, right? So AC is a vector quantity. What is it? What is the difference between a scalar and a vector quantity?
The direction must be specified.
Yeah, both direction and magnitude
dependent.
has to be specified, right? We know that for a DC, definitely there will be only one direction to flow, and whereas for AC, definitely it should be having certain magnitude, right? And also the direction, right? So how do you represent these vectors? How do you vector, or you call it as a phasor, right? So how do you represent these AC quantities then? AC quantities can be represented with vectors. So how do you represent a vector? And see, if I have a sinusoidal voltage, suppose say I have a source, I fed this to a resistor, right? Let us derive this practically later on, but let me write the equation for V and I. What is the equation I can write for V and I? Is Vm sine omega t, as we learned in the morning class. What is I? Is Im sine omega t, right? So if forget about the magnitudes, if suppose this is a voltage and current has to represent here, if this is the value of V, and how will the value of I will be? Just like this, right? So this is I. So what is the parameter which makes it to draw like this? Why can't I draw it in some other way?
It is in phase with voltage, sir.
Yeah, why can't I draw something like this or like this? Because the equation suggests that they are having same characteristics of sign. There is no phase difference, there is no difference in the sign terms. So the value of starting and in angular velocity is remaining same, So they will start and end at same points. That's the reason why I have to drawn like this, right? The same quantities can be represented in phasors or vectors just like this, where just like a straight line, right? Where length of this uh, vector, represents the magnitude, and the angle difference with particular reference will give the phase angle. Suppose if I am taking this as a reference, right? Now the voltage and current are falling on the same reference. This is B, and on the same value I have I, right? We'll study about what is the difference I have for these vectors and phasors, right? So whenever it comes for addition of solar vector quantities, it's a vector addition, right? I will tell how it happens, but just see the waveforms here, A and B. If this is the waveform A, right? So this is a waveform A and this is waveform B. If at all I can add them, this is a waveform C, A plus B. Right. This is how we add the see, when it comes for a DC quantities, it's an algebraic sum. But when it comes for AC, it generally will be a vector sum. See, suppose if this is A and B, right? This all quantities are vectors in nature. So definitely they, you know the difference between algebraic sum and a vector sum, right? So definitely the sum will not be same as algebraic in vector, right? So let me explain how it happened. So let me come back for this. So what is the need for radian or else angular velocity? So the radian angle representation, omega t, is the only mathematical formula seems to be suitable for representing a sinusoidal varying quantity as a function of time. In that it can describe their instantaneous magnitude at any time in a simple way, right? So instead of writing in terms of theta, we'll write in terms of omega t actually, right? And what is omega? Is a 2 pi f. Omega is equal to 2 pi f, or it can be also written as, you know that f is already, what is f? 1 by t. So I can also write it as 2 pi into 1 by t, right? Now, see, I think, okay. What's the difference between radian cycle and what this mean is? Okay, this animation yeah. See, time is going on increasing, but the radians, right, omega and v, that is frequency, are remaining constant. What does it indicate? See, if I rotate the conductor for one cycle, what happens? What happens if I rotate it continuously? What happens if I go on continuously rotating it? Will the angular velocity go on changing? The radians, right? Omega value 2 pi f remains constant actually, because nothing is variable there, right? 2 pi is for representation of vector in a circular formation or for circular rotation, and f is a frequency at which it is rotating, the velocity at which it is rotating, right? What's it mean by frequency? Cycles per second. That's the speed, right? At which the vector rotates. So we are considering a sinusoidal waveform, right, to be represented with a phasor. But what do you mean? What's the difference between a phasor and vector? I already said this in the class. What's the difference between phasor and vector? Assume that this is a vector here. This as this rotates, right? You call it as a phasor, or a rotating vector is nothing but a phasor, right? So I'm just want to represent this sinusoidal waveform with a vector, right? Just like this. I will show it which. Like this. Yeah. See, this is a, see, figure I. What does the figure I represent? What is figure I is representing is a complete sinusoidal waveform, right? So let us go for how we develop the sinusoidal waveform from 0 degrees to 360 degrees, right? So let me take instant from 45 degrees each. So at 0, at alpha is equal to 0 degrees, the vector is lying on the reference, right? So the magnitude of this is 0. Now as it rotates in a anti-clockwise direction with 45 degrees, why I'm taking anti-clockwise direction? Because I have realized a sinusoidal waveform just now previously. How did we realize? From position 1 to position 2, 2, from position 2 to 3, 3 to 4, we are moving in anti-clockwise direction. Same way I'm just taking here for representation. So vectors are assumed to be rotating in anti-clockwise direction. So I just took that if the vector rotates by 45 degrees, I know I already said you this magnitude represents what is the vector, this length represents what is the length of the vector represents is a magnitude, right? So now if this vector is at 45 degrees, this is a magnitude that it is going through, right? And if it is at 90 degrees, it is, has completed maximum value. Now when it moves to 135 degrees, it is coming down, and 180 degrees, it has completed first half cycle, right? If the phase is increased to 225, it has gone to negative. Next 270, it comes to negative maximum. 315 and 360, the complete cycle is formed. So this is how the vectors are represented. That means a complete cycle of vector will a complete cycle of alternating waveform. So I can represent a vector with a rotating I can represent a AC quantity with a rotating vector, which is nothing but a phasor, right? Just a representation of phasor quantities, right? Now see, whenever I have a phasor with respect to some reference, I can represent them with these two terms. What is this? See, what is the difference between these two waveforms? They both are alternating in nature. Instead of writing sine omega t, I have some terms to add here and subtract some term here. What is that? Why should I add it as plus theta and minus theta here? See,
Phase difference,
waveforms?
initial phase difference.
Yeah, they're not starting from 0. Suppose if this is the reference, if this is the reference, right? The waveform was already existing before this reference. And see here, if this is considered as reference, the waveform is coming after certain predefined time or certain time after certain time or certain angle, say, right? Suppose if this is coming after theta, time theta, right? I have to mention it as minus theta. And if it is already existing before the reference, then I have to add it with the angle plus theta, right? So which one is considered as leading and which one is considered as lagging with respect to reference? This is considered as leading, right? This is considered as lagging. So if I have it plus or minus, what does it indicate? Lead or lag. Am I clear? See, there is a simple representation here. If a sinusoidal waveform voltage, if a sinusoidal waveform which has a 90 degrees leading characteristic is equal to a cos wave. So simple as that, right? Or the same sine quantity can be represented in terms of cos omega t minus 90. Both are one and same, right? I can move this forward by adding a leading angle of 90 degrees, right? What is it equivalent to? Same values, right? Sin omega t plus 90 can be written as cos omega t, or sin omega t can be written as cos omega t minus 90. This will be useful while you write the equations for alternating quantities, right, in inductor and capacitor. So these are some examples where I can show you is see, voltage is represented as, what is this representation mean?
Amplitude.
Yeah, V is equal to V max sine omega t plus theta, or else plus some value 30 degrees, right? And what is I? I am sine omega t plus theta, or else I say it as theta 1, theta 2, right? So how do I represent these two terms in a waveform, representation of waveform? See, in the previously what we have learned is we took one as a reference. What is the other way to write this? I will just explain it. But how do you represent them? What is the way you represent these two? In the equations, what it is given? Voltage plus is leading, right? Voltage is leading by 30 degrees. Current is leading by 70 degrees. Then what is that reference which we are taking? How do you draw that? Is just like this. If this is the reference, right? If this is considered as reference, voltage waveform starts 30 degrees before that, whereas current waveform starts 70 degrees before that. What is the reference? We are taking this vertical y-axis as reference. Now, what is the best method to represent if at all I take voltage as reference now? If I want write to, what's the other method we can write is I take this as a reference. So now what is the equation for I then? I am sine. What is the equation you can write here?
Omega t plus phi.
Omega t plus, what is the magnitude of pi?
Plus 40.
Yeah, we can take it as 40 because we are taking V as a reference, right? So now whenever I take V as a reference, this is the starting point now. This becomes 0. This point becomes 0. And what is the current that is leading here is only 40 degrees. So I add here. So you can represent the same thing with two different equations here, right? I can represent here like this, or I can represent here in this sense. So whenever you say V is equal to Vm sine omega t, no need to mention it as a reference. It's already known that. It's already given that V is considered as reference. Am I clear? And what is the need why we take only voltage as reference? Why don't we consider current as reference then? What happens if I write this current as reference then? Why there is no thumb rule that we don't write I is current in terms of or else reference in terms of current. So let me take it as sine omega t. I take this as reference. What's the value of V I has to write? Same for same waveform. What should be I write for V? The representation remains same, right? Vm sine. What is the
Omega
equation?
t minus 40.
Yeah, minus 40.
40.
So what can I write? Say now voltage is lagging current by 40 degrees, right? But there are certain thumb rules, right? What does it indicate? There are some common rules, not thumb rules. There are some common rules which we follow that we generally take V as reference. Always the quantity in terms of V and I. If I have two components, what is taken as reference is generally V. That's the reason why we talk in the inductor and capacitor. The current lags the voltage, current leads the voltage. Nowhere we talk it as voltage leads the current or voltage lags the current, but usually what we use is current lags the voltage or current leads the voltage. Is that clear? Yeah. Now let us go for the case B. What is the case B? I leads voltage by 80 degrees or V leads lags the voltage by 80 degrees. See, what was the equation given here? The equation given was I is equal to 15 into sine omega t plus 60. V is equal to 10 into sine omega t minus 20. So how do I represent? How can they be represented? One is plus 60, another one is minus 20. So this is the complete representation, isn't it? So as a whole, what's the equation I can write if I take V as reference? If I take V as reference, what's the equations we have to write? V is equal to Vm sine omega t. What's the equation I write for I then? Is I lagging or leading compared to V? Comparing this as reference, is the current leading or lagging?
Lagging.
This is a voltage curve, right? Leading. Yeah, this is a voltage curve, right? దీనికన్నా ముందే ఉండిపోయిందంటే ఆల్రెడీ అర్థమేమి current is leading the voltage, right? Am I clear? Current is leading the voltage by what's the angle I have? It was 60 by I. Already current was leading a reference by 60 and voltage was lagging 20 by the reference. So what's the equation I can write? I is equal to I am sine omega t minus 80 degrees. Is that okay?
Yes, plus 80.
Yeah, that's good. What do you write it as? Plus 80. Why? Leading gives plus is given for leading, right?
Yes.
Very good. So this is what we represent, how we represent for voltage and current. Okay. Similarly, you have one more example, many examples. We can go through them. Right? Done. So we'll learn about the average and RMS values in the next class. Okay. Tomorrow we have the lab in the afternoon. So first 1.5 hours we'll be talking about the lab for a theory subject, and next we will be talking about the lab. Okay. Is that okay for today? And any doubts? Okay then, if you have no doubts, then thank you for today.
Yes, sir.